Let's get started. There are some imports here. These first two lines make you use the full width of your browser. We don't need it now because we're on lab. It's already using the full width, but it can be useful for your future self. Then we have general OS imports, NumPy, SpecViz. It's here, so import JDAViz, and from JDAViz import SpecViz. I usually import the full package before just because I want to check the version later, and you need this to check the version later. AstroPy, some Specutils functions that we will use later, and some customization for Matplotlib. Run this cell. We have the imports. Run the cell next after that, and we get the versions. As I said, is JDAViz 2.0.0, the latest, and also Specutils is pretty recent with its 1.4.1. Let's fetch the data. We are downloading them from Box, and here we have 3 files. One is the same near spec spectrum that you saw before. Then you have a mystery spectrum. We may or may not get to the exercise today, but just in case you have it there, and I'll talk a bit about that later if you want. And then you have a template spectrum, because for the Redshift fitting and for the template fitting, you need templates. And these are a combination of simple star population models of galaxies. You can check the paper for the details if you want, but you can also use any template model spectrum you want for this. So let's do a first Redshift measurement by eye. So we open SpecViz, we call SpecViz, and then we do viz.app, and we open the app. So let's familiarize ourselves a bit with the app before. As you can see, it's just one viewer. You have an import button here if you want to import files that are in your computer now. Well, now you're in the platform here, so you can import files that are in the platform now. Then you have the region selection piece here on top. Then you have the Redshift here on top that we will be using later. If you click on this, you'll see that there is also radial velocity. As I said, you can adapt this workflow to other science cases. This Lego button brings the plugins to you. We have 5 plugins in SpecViz. The data button here will show you whatever data you have already loaded in the tool. There is nothing now. And here you have the hammer and screwdriver for zooming and panning and selecting regions, and the layer that now it's empty because there is nothing in there, but I'll show you, you can use that one too. And since this is a tool in development, this button does absolutely nothing, so you can use it if you're fed up or whatever. It does nothing. So let's load the spectrum. So we do as simple as load spectrum, and we feed in the file name that we just the file that we just downloaded, and we give it a name so that this is the name that shows up in the data tab that I showed you before here. Okay, and here it is. So it's the same spectrum we saw before. Green snack bar message shows up here telling us that the data was loaded successfully. You can wait or closing it. So now we want to measure the redshift of the source. And to do that, we need first to plot some lines on this plot. So we can go to the Lego button, and then I would like to do this as interactively as possible, or at least that's what we would do if we were in person. So I'll let you guide me. We need to plot lines, so we need to find the line lists. So I opened a bit the tray so we can see it better. Then we have another menu here, and if we click it, we open the available line lists, and these are a lot. You can check what we have here, and we hit load list to load the list. Okay. Oh, a snack bar message told us that everything is fine. We go down and we see the loaded lists here. So there is a custom line here where you can actually input your own lines, but we loaded the common nebular, so let's just use this one. And we open the tray. Now we see some customization for the color in which we can plot the lines, and then we see a long list of lines. So let's do H beta, O3. We go to H alpha, and we have the 2 nitrogens, and H alpha, and sulfur. We do all of them. So I clicked a bunch of lines, but nothing is showing, as you can see, because they are being plotted in ResFrame, and our plot doesn't cover ResFrame there. So we need to give the tool a guess of Redshift as a start. So let's imagine you set 1.6. So the lines are slightly offset compared to the observed lines. We can use this slider to match the lines with the observed lines. And this is our Redshift by eye. So let's do the Redshift measurement with cross correlation. Now, this is very common algorithm to measure Redshift, and it is built in Specutils, follow the method that is in IRF for cross correlation. So it works in the exact same way. And what you need for this is to get a template spectrum for the correlation. Then you need to bring the template spectrum and the observed spectrum on more or less the same flux range. So you either subtract the continuum from both, or you can normalize the spectrum to the same integral. And in this case, I'll show you the method normalizing, subtracting the continuum. And then you have to make sure that the 2 spectra overlap in a wavelength range. So let's open the template spectrum. So first we define the units. Not that it matters much for the correlation per se, but you need a unit to read it in as a Spectrum 1D object. So we'll do the proper way. And it's an F lambda unit. Then the spectrum is an ASCII file. So I'll just use the ASCII read function and call the template file name. And then I create the Spectrum 1D object. So I will just go Spectrum 1D, then the spectral. I created this ASCII file, so I know exactly what's in there. And I know that column 1 is the spectral axis, and it's in angstrom, so I just divide by 10 to the 4 to get it into microns. I could also read it in angstrom and then do the wave unit conversion as Eric showed you. But this is just one additional 10 to the 4. And the flux is is column 2. So I just read it in and I add the spec unit that I defined before. So I have my template spectrum. Then this is a very large wavelength range, this template. So I create a mask to only use the part that I care about. I don't want to carry around a super big spectrum. Spectral axis, value, and we keep it only between 0.3 and spectral axis value 1.1. And then we create another Spectrum 1D object applying this mask. So we use the spectral axis. As spectral axis, we use the template spectral axis because it is the same spectrum, but we apply the mask. And same thing for the flux. So for the flux, we have the template flux and apply the mask. Here we are, and we can look at the spectrum. This is pre-populated. It's pretty common to use matplotlib to plot stuff. So this is our template. Now to subtract the continuum, it's best to mask the lines. The continuum will be better if we mask the lines. So I have a pretty big mask here to go around these lines. So I don't write it out again, but you saw how it works. So this is the mask to only keep like this range, this range, this range, and this. And then I create another Spectrum 1D object applying this mask now. At this point, we can call the fit generic continuum function on the template for continuum spectrum that we just defined. And we tell the function what model we want, and we want a polynomial 1D of 5th order. You can play with this. It's not critical to get the perfect continuum here. You just need to bring everything to 0. Then we apply this function to the spectral axis of the original spectrum, which is what we want to use. And we can do the math of taking the spectrum and subtracting the continuum. Here we go. We can check the Spectrum 1D object. All fine. There's a flux with the correct units. There is the spectral axis with the correct units. And we can look at the spectrum. As I said, it's not critical that the spectrum has a perfect continuum, you see here, but it's totally fine for our purposes here. At this point, we can do the same thing for the observed spectrum. So we read it in as a Spectrum 1D object. In this case, we don't have to do any magic because there is a reader for fits files and especially for JWST files. So just a Spectrum 1D read will do the trick. But we need to add the uncertainty because it's not in yet. This is a simulation. I'm using the tab here. So we do Spectrum 1D, spectral axis, and then we take the flux, and again, it's the same flux. Oops, sorry, spec 1D flux, but then we add the uncertainty. So we do uncertainty is equal the standard deviation and we define it as 5% of the flux. We'll close all the parentheses we need to close. And then we define a region. Now, to define a region, you can also use the spectral region function. And just, it's equivalent to defining a mask. It's just another way of doing it. 1.6 micron units. And then you can extract that region of the spectrum where you want to run your continuum function. So you just do extract region. And it's from the spectrum you want. And the region, we call it region. As simple as that. Now we can call again fit generic continuum. Continuum, and we call it on the Spectrum 1D for the continuum that we just extracted, and we use a linear model this time because the spectrum, we saw it before, it was pretty linear. Just like this, and then we fit the observation. We apply the continuum to the spectral axis. The continuum calculation to the spectral axis. And we can do Spectrum 1D minus continuum obs. We run this. Here we were printing the spectrum here because I wanted to show you that the uncertainty is populated now. And we can go and plot our spectrum that is now with no continuum. Continuum is at 0. You can also do the same thing using SpecViz. So this is another option for later if you want to do the exercises. You can fit the continuum using the GUI. Select a region and then do the model fitting. And it will remind you of the same thing we just did with the spectral region. So now we can run the cross-correlation function. And to run the cross-correlation function, we call correlation dot template correlate, and we have the Spectrum 1D without the continuum, the template without the continuum, And we need to specify the lag units. It's Redshift, so it's unitless, so it's just U.1. You can use also dimensionless unscaled, but it's super long and prone to spelling mistakes. So there is this convenient 1 instead. We can run this cell. Oops, you see, spelling mistake? Correlate. Okay. And here it is plotting the correlation, the redshift, the correlation versus the redshift. And we see a big spike here, which is probably our best redshift. So we call NumPy argmax on the correlation, which gives us the index of the best, of the highest peak. And then we call the lag on that index. And here is our redshift, so 1.501. So we were very close. Vivian was super close when we did it by eye. So this is the correlation, and you saw how fast it is also. It only uses one template, and it's super fast. You can also get an uncertainty on the redshift by looking at the width of this peak, for example. There are other ways also. There are not just for returning a redshift, but also for matching your observed spectrum to a template spectrum by a full spectrum fitting via chi-square. So this by no means wants to be a substitute for an SED fitting tool, because it just returns the best template and it doesn't return any uncertainty on it. But it's a good first step to see if your templates are a good match for the observations you have. So we have to download a library of templates. So click over this cell, Shift Enter. It will download the library on the platform. And while it does that, we can create the list of Spectrum 1D objects from the template library. If you don't mind, I'll copy over this, the way the ID is written in the for the file, the file name. It takes the template directory that we define here. That's where the files are written, and the index. And for in the interest of time, because it takes probably 2 minutes, but it's still we can save some time. I'm just taking 10 files instead of the 100 that are in this template library. But this template library stays for you. If you want to use this Spectrum, this notebook, it will just pull out the entire template library, and you can use it for your own science as well. So we do the ASCII read that we did before, template file, and then we create the Spectrum 1D object just like we did before. The spectral axis is template column 1. See, it's exactly the same we did before, times micron, and the flux is template column 2 times the spec unit that it's saved from before, didn't forget. And to build a template list, we append temp 1D. So this will run for a little bit, and in the meantime we can start populating how the template match function works. So you can either define a redshift range with a minimum redshift, a maximum redshift, and a delta redshift, and then create a NumPy array with those redshifts, or you can use a fixed redshift. So the time it takes for this function to run highly depends on the number of templates you have and the number of redshifts you want to try. So in this case, we'll just use the fixed redshift because we know what the real redshift is. We just did it with the cross correlation function. If we didn't do that, we would probably use the z values on a certain range. And since the function needs to resample the spectrum, we'll use a flux conserving resample. So we call the function here by calling template comparison and template match. There are other functions. There is also a template redshift, which returns only the best redshift. It doesn't really care about many templates. It just uses one template. Anyway, there are different. There are links to the documentation here, so you can check it yourself later. We need to give the observed spectrum, which is our spec1d. Then we need to specify the spectral templates, and it was the template list that we just defined before. The resample method, it's the resample method we just defined just before, and the redshift. And we use the fixed value, which is this ZZ that I defined before. So we run it. It doesn't take too long because it's only 10 spectra here. It will take much longer if you use the full library. Once that is done, we can print the results, and then we can open another instance of SpecViz and visualize them. So I can start populating these cells while it's running. It will open the app, and then here we load the spectra. Is the spec1d, which is our observed spectrum with the data label as observed spectrum. And this one is the template spectrum. Oh, this is done. Okay, perfect. So I can show you the results. And the results are a spectrum1d object that is the template already redshifted and normalized to your spectrum, the best chi-square, and the ID of the best chi-square, and the list of chi-squares. So since we have this spectrum ready to be used, we take the results, which is what I just plotted, the 0 element in that list, which is a spectrum1d object. And for data label, we write redshifted best template. Okay, so now let's run SpecViz again. It's a second instance of Viz2. You can say call it in a different way, but it's the same as before. And then I load the two spectra, and here they are. So now they're both in gray, one over the other, so we can't see it very well. But we can go to the Layer tab, select the spectrum we want to modify first, and change the pixel size, change the color. We can make it black. Just click down here, make it black. And then we can go to the redshifted best templates, change the color as well. I like to make it purple here, and maybe a bit bigger as well, thicker. And you see how nice it is. It's well normalized and it matches perfectly the lines. This is what I had for the three methods to measure the redshifts with VizTools or with Specutils.